Hello everyone. In today's lecture, I'll be discussing about linear programming problem. Linear programming is an optimization method applicable for the solution of problems in which the objective function and the constraints appear as linear functions of the decision variables. So already in the previous classes I have discussed about what is decision variable, what is objective function. So in order to thoroughly understand this lecture, you need to go through the previous lectures so as to get the meaning of the basic terms like objective function, decision variables, etc. So the constraint equations in a linear programming problem may be in the form of equalities or inequalities. The linear programming type of optimization problem was first recognized in the 1930s by economists while developing methods for the optimal allocation of resources. During World War II, the US Air Force sought more effective procedures of allocating resources and turned to linear programming problem. George B. Danzig, who was a member of the Air Force group, formulated the general linear programming problem and devised the simplex method of solution in 1947. Although several other methods have been developed over the years for solving linear programming problems, the simplex method continues to be the most efficient and popular method for solving general linear programming problems. Among other methods, Karmakar method, developed in 1984, has been shown to be up to 50 times as fast as the simplex algorithm of Danzig. So what are the applications of linear programming? Basically, the number of applications of linear programming has been so large. I'll be discussing few applications here. Like it is used in the food processing industry. In food processing industry, linear programming has been used to determine the optimal shipping plan for the distribution of a particular product from different manufacturing plants to various warehouses. In the iron and steel industry, linear programming was used to decide the types of products to be made in their rolling mills to maximize the profit. Metalworking industries use linear programming for shop loading and for determining the choice between producing and buying a part. Linear programming has also been applied to formulate and solve several types of engineering design problems such as the plastic design of frame structures, etc. So there are various other applications also which you can find in the books that I have prescribed for this course like S.S. Rao and all. Now moving ahead to the standard form of a linear programming problem. So the general linear programming problem can be stated in the following standard form. So it can be stated either in the scalar form. These two are the standard forms like scalar form or in the matrix form, whichever form you choose. Both the forms that I have shown here, they are the standard forms. So as you can see, in the scalar form, fx, that is f bracket x1 x2 up to xn, this fx is the objective function, then it is equal to C1 x1 plus C2 x2 plus dot 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 Cn xn, where x1 x2 x3 up to xn are decision variables and C1 C2 C3 up to Cn is the constant values. So subject to the constants, here again I am repeating that fx is the objective function. These are the equality constants, that is a11 x1 plus a12 x2 plus dot 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 a1 n xn is equal to b1. Similarly a21 x1 plus a22 x2 plus dot 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 plus a2 n xn is equal to b2 up to am1 x1 plus am2 x2 plus dot 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 amn xn is equal to bm. These all are equality constraints. So here from these equality constraints you can see that there are m number of equality constraints and the decision variables, that is x1 x2 x up to xn. So there are n number of unknown variables, or you can say n number of decision variables, and the decision variables are all greater than or equal to 0. In matrix form also I have written these equations we can write these equations in the matrix form like this. Minimize fx is equal to ctx, where x is the n-dimensional vector, that is x1 x2 up to xn. Then it is subjected to the constants ax is equal to b. Nothing, just these equations have been written in the matrix form, where x is the n-dimensional vector, b is the vector of all the constants, and c, they are the constant values. Again a is also written in the matrix format from these equations. So yes, all the objective, as you can see from this scalar and matrix form, that all the objective function, equality and inequality constants, here I have shown only the equality constants, that is all the objective function equality constants in this optimization problem are linear in nature, that is the power of x is 1. And therefore the problem is the linear programming optimization problem. So here in this optimization problem, in linear programming, this optimization problem, I have mentioned the constraints, that is equality constraints. But if any optimization problem there is no equality constraint or inequality constraint, then that type of optimization problem is called unconstrained optimization problem, that I have also discussed in the previous classes. Now, as you can clearly observe from the scalar and matrix form of the standard linear programming problem, the characteristics of linear programming problem are: point 1, the objective function is of the minimization type. As you can see, the objective function fx is of the minimization type, minimize fx. The second point, the second characteristic of linear programming problem is that all the constraints are of the equality type. So as you can see here, all the constraint equations, they are of equality type. And the third characteristic of linear programming problem is that all the decision variables are non-negative. Exactly as you can see from scalar and matrix form, that x1, x2 up to xn, these decision or unknown variables, they are greater than or equal to 0, means they are non-negative type. Now moving ahead with the next slide. Now any linear programming problem can be expressed in the standard form by using the following transformations. So I have told you about the standard linear programming problem, but if the linear programming problem is not in its standard form, then we need to do certain modifications on that problem and can convert it into the standard form. So what are the modifications? Let me tell you. So as I have told you, the first characteristic is the linear programming problem objective function would be of minimization type. But if the optimization problem is not minimization type but is of maximization type, For example, the maximization of a function f x1 x2 up to xn is equivalent to minimization of the negative of the same function. So if an optimization problem is a maximization type, it can be converted into the minimization optimization problem, just as we know maximization of a problem or function is equivalent to minimization of the negative of the same function. That is, I have shown here clearly, that is, if the question comes out to be like this, that maximize 3w plus 2p, and there are certain constraints in that optimization problem, then you can convert that maximization problem into minimization problem just by using a negative sign, which means this maximization problem has the same optimum solutions as minimize minus 3w minus 2p subjecting to the same set of constraints. So this is the first transformation we can do when the optimization problem comes out to be the maximization problem. So yes, the next characteristic, so as I've told you that objective function should be in the form of minimization problem, and convert this maximization problem to minimization problem by minimum f is equal to minus of f dash, where f dash was in the maximization problem. So the next characteristic, as I've told you, that if the decision variables, they should be of non-negative values. As I've told you, the characteristic of linear programming problem, that all the decision variables are non-negative values. But if decision variable xj is unrestricted in sign, it can be written as xj is equal to xj dash minus xj double dash, where xj dash and xj double dash both are greater than or equal to 0, and depending upon the sign of xj, xj double dash can be greater than, equal to, or less than xj dash. So if the decision variable is negative, then what we will do, we will make xj is equal to xj dash minus xj double dash, where xj dash and xj double dash both are greater than 0, and xj double dash will be greater than xj dash. So in this slide, I've shown you what I'm trying to say. For example, there is a optimization problem, that is maximize 3x1 plus 4x2 plus 5x3 subject to the constraints 2x1 minus 5x2 plus 2x3 is equal to 7, and there are various other constraints also that I have not shown in this. And the decision variable x1 is less than or equal to 0, but x2 is unconstrained in sign, and x3 is greater than or equal to 0. So I can transform x2, that is, I will replace x2 by y3 minus y2, where y2 and y3 will be greater than or equal to 0. So as basically how this thing came, in most engineering optimization problems, the decision variables represent some physical dimensions, and hence the variable xj will be non-negative. However, a variable may be unrestricted in sign in some problems. So in such cases, an unrestricted variable can be written as the difference of two non-negative variables. So if given x2 is less than or equal to 0, that is x2 is negative, that is decision variable for inequality constraint, then we'll represent x2 is equal to x2 dash minus x2 double dash, or here I have written it as y3 minus y2, where y3 and y2 would be greater than or equal to 0, and this y2 will be greater than y3. So by doing this, the number of unknown variables, initially it was in the terms of x, but by using y2 and y3, the number of unknown variables in the constant equations will get increased. Now, the third characteristic is that, as I've already told you, that the third characteristic of linear programming problem is all the constraints are of the equality type. But if the constraints are not in the form of equality type, if they are in the form of inequalities, so how you will convert those inequality constraint equations into equality? So this thing I've shown in this slide. That is, if a constraint appears in the form of less than or equal to type of inequality as given here, ak1 x1 plus ak2 x2 plus dot 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 ak and xn less than or equal to bk, it can be converted into equality form by adding a non-negative slack variable xn plus 1 as shown. That is, ak1 x1 plus ak2 x2 plus dot 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 ak and xn plus xn plus 1 is equal to bk. So what I have done, I have transformed this less than inequality constraint equation into equality constraint equation. Similarly, if the constraint equation is greater than or equal to types, I can convert it into equality constraint equation by subtracting a variable. Here I have subtracted a variable xn plus 1 from the equation, and this xn plus 1 is a non-negative variable and is known as surplus variable. So as you can see from these slides, that if n is greater than m, what is n? N is the number of unknown variables, or you can say n is the number of decision variables. That means x1, x2 up to xn. I've already told you in the previous slides. So this n number of decision variables, if it is greater than n number of equality constraints, m is the number of equality constraints. I've already mentioned in the previous slide that there are m number of equality constraints and n number of unknown variables. So if n is greater than m, then we have to choose some variables as dependent variables and some as independent variables. So we need to choose m number of that is m number of dependent variables and represent them in n minus m independent variables. Now, so if n is greater than m, then that type of optimization problem have infinite number of solution, as the combination of the result depends on selection of n minus m variables. If n is equal to m, then we get a unique solution, and if n is less than m, if n is less than m, then we get unbounded solution. That is, on getting m number of variables, these n solutions may not satisfy remaining m minus n number of equations. So in the next slides, I have shown you that how you can convert the inequality. That is the third point I have shown in the next slides, that how you can convert an less than or greater than inequality constraint into a equality constraint. So before, as you can see in these slides, that before the equation, that is inequality constraint equation, was less than type, and using a slack variable, and by using a slack variable s1, we have converted into a equality constraint. Similarly, we can also convert inequalities into equalities plus non-negative resources. That is, if the right hand side is the negative, then we can eliminate it by using a negative sign in the left hand side. That is, transferring the negative sign from right hand side to the left hand side. And last but not the least, that we have converted the greater than or equal to constraint into equality constraint by subtracting a surplus variable from the equation. And as it can be seen here s2 is the surplus variable, and it has been subtracted to convert the inequality constraint to the equality constraint. So in the next slides, I will be coming up with the questions and solutions to how to solve this linear programming problem. So I'll be ending this class here. We'll continue in the next class.